This is the science of thermodynamics in action. The science of heat transformed into mechanical energy. The power-driven machinery of the Industrial Revolution depended on it.
Heat energy can be turned into the energy of motion, such as by turning a crank or a piston or a turbine to be used to pump water, to turn a loom to make fabric, to move a boat through the water, to move a train down rails. Now, it's desirable to get more oomph for your dollar, to get more work done for the amount of fuel you're going to use. And so people began to study how heat engines, how steam engines really work.
Among those who studied it was a German scientist named Rudolf Clausius, who in 1865 formulated our next great discovery, what became known as the second law of thermodynamics. The law states that in any energy exchange, such as heating the water in a steam engine boiler, some energy is always wasted. Clausius coined the word entropy to explain why the efficiency of a steam engine is limited, because some of its energy will always be lost in the process of converting it to mechanical work. It was a momentous insight, one that changed our understanding of how energy works.
There's no heat engine that is 100% efficient. When a car is moving along, how much of the energy implicit in the gasoline that you put into a car actually gets used to move the car and you in it? Only about 20%. Where does the rest of it go? It goes to heating up the pavement on the road, heating up the tires. The cylinders in the engine block get hotter. They wear out. Parts corrode. It's sobering to think how wasteful these processes are.
While the second law of thermodynamics was a driving force behind the Industrial Revolution, our next great discovery powered the world into the modern age. It's one of the great engineering feats of the 20th century, the Hoover Dam. 726 feet high, weighing 6.6 million tons. The dam's 17 generators produce nearly 3 million horsepower of electricity. Electricity created using a magnetic field. Scientists had figured out how to create magnetism with electricity by running an electric current through loops of wire. The result is an electromagnet. Turn on the electric current, and a magnetic field is created. Turn off the current, and the magnetic field disappears. In 1831, a bookbinder with an interest in electricity named Michael Faraday was first able to reverse the process using a moving magnetic field to create electricity. An electric generator, in its most basic form, is just a coil of wire between the poles of a magnet. Michael Faraday discovered that when the magnet and the wire move near each other, an electric current passes through the wire. Every electrical generator works on this simple principle. Faraday kept somewhat cryptic notes on his experiments, but years later they proved invaluable to a physicist named James Clerk Maxwell, who used them to contribute to our understanding of how electromagnetism works. To find out more about this discovery, I paid a visit to the Museum of Science in Boston.
Bill Nye, this is great. So what is this device?
Well, this is a generator, and we use it here at the museum to talk about lightning and lightning safety, and a little bit of what you were just mentioning, that sort of connection between electricity and magnetism. We've got this demonstration, this sort of giant bird cage, and we can use that to show how electricity and magnetism are sort of interrelated. Would you like to try it?
Oh, yes, of course.
Well,
one test is worth 1,000 expert opinions.
After you.
One of the things Maxwell helped us understand is how electromagnetic fields are distributed on a conducting surface, like the metal this cage is made of.
And now, if you want, when I start to make some of the sparks, if you put your finger on the inside of that bar, you should be okay. If you want to give it a try.
If Maxwell was right, the enormous 1.5 million volts of electricity created by these generators will distribute itself nicely around the outside of the cage and not be able to penetrate the inside. Right now, I'm hoping James Clerk Maxwell was right.
You ready?
Yeah.
Well, go ahead, put your finger up there, and we'll give it a try. Here we go.
It is spectacular. So, what's happening? The electricity is hitting the cage, and that's creating a magnetic field?
That lightning bolt is a current of electricity. It strikes the cage, and that turns the entire cage into sort of a giant magnet. The magnet, in turn, makes another electric field. And that electric field around the outside of the cage pushes all the electrical current to the very outermost surface.
Yeah, it's amazing. Well, thank you very much.
Well, thanks for coming.
I'll never forget that. That is just spectacular. I'm fine. If you want to know what the world would be like without the work of Faraday and Maxwell, imagine a world with no electricity. There'd be no radios, no television, no cell phones, no satellites, no modern communication of any kind, no computers. Think of being in the 19th century. That's where you'd be. Now, what Faraday and Maxwell couldn't know was that their discoveries would inspire a young man who would go on to unlock the secrets of light and its connection to a fearsome power in the universe.
In 1905, the scientific world was turned upside down by our next great discovery, one of several revolutionary theories put forth by a young, unknown scientist working in a patent office in Bern, Switzerland. His name? Albert Einstein.
Believe it or not,
To find out about Einstein and his discovery, I paid a visit to Michio Kaku, a physicist at the City University of New York.
Einstein once said that all ideas should be presented to children, and if children can't understand it, the theory is worthless. When he was a child, he read a children's book. Electricity was just coming in at that turn of the century, and people were fascinated by telegraph wires. And there's one book by Mr. Bernstein that says, imagine yourself racing alongside a telegraph signal inside a wire. That's where we think, historically speaking, Einstein got his earth-shattering idea, from a children's book.
When Einstein was a teenager, he was inspired by his memory of the children's book to imagine what would happen if he was riding on a beam of light. He pondered that idea for the next 10 years and began thinking about light, time, and space. He realized that Newton's theory that space and time were fixed and absolute did not apply as you approach the speed of light. From this insight, he formulated what he called the special theory of relativity.
In Newton's world, space and time were always separated. If it's 10 o'clock on the Earth, it's 10 o'clock on Venus, it's 10 o'clock on Jupiter, it's 10 o'clock throughout the universe. Time was like an arrow. Once you fired it, it never came back, never deviated. Einstein comes along and says, not so fast. Time is like a river that meanders around stars and speeds up and slows down. Now, of course, if space and time can change, that changes everything. Everything we know about atoms, everything we know about our bodies in the universe changes once time and space also change.
Einstein demonstrated his theory with what he called thought experiments.
The most famous thought experiment is the twin paradox. You get two twins on the Earth, you put one in a rocket ship, send that person off, and of course, that person accelerating near to the speed of light, his time slows down. And so when the two people come together, the twin in the rocket ship is younger than the twin on the Earth. Time beats at different rates throughout the universe.
Depending on what?
Yeah, depending on your velocity. The faster you move, the slower time beats.